So it was shaped. So maybe okay.
What's happening today? Why is everything like this today?
Sometimes is that
This is the whole extract. Ah,
I thought because I know right now.
oh, they're starting. We actually can.
Maybe one not. I can just show.
it's better to
Zoom is already on.
Oh, sit in the thing.
right.
I see.
I don't know whichever way.
I've never used.
I'm just showing same screen, but I have to stay here because the camera is here. So not necessarily I will show. I can try because I don't know the future. So because I need to test.
We actually have face-to-face
Test.
class for this one now.
What?
I hear the. Oh.
Oh, okay.
Let me try how this way works.
Can you see? This session should be Ishibashi. Can you see?
Yeah.
Is that him? I have never actually met him before, so I don't know
really?
what he looks like.
The only problem is right. If I do this way, maybe Zoom is better.
This way. Maybe Zoom is better.
What you guys using Zoom? Is that logging or not? Because the video would be because I use video, but would be like because I'm doing from here, I cannot show same time to PowerPoint here. Not allowed.
That or
We don't have a so. Yeah, I have to separate the control. So ideally, if you guys can on with Zoom, is better, so that you can see what's going on. Not using this is better.
Is it? It's okay. Because it's still kind of yellow. Oh, I don't have the BB thing.
So
there's nothing in here I can.
Sorry for the Zoom people in Zoom because you know like we are doing mixed mode, so it's a bit conflict between Zoom and the people who attend in the classroom. So little I need 1 or 2 more minutes. This need to get this.
Finish this one.
I don't like the bottle.
Ah, I see.
Is that okay to turn on the Zoom? Zoom? Yeah, because I think some movie or something like when I use, actually I have to control from here. So the Zoom people to do, then I can control the same answer. Thank you. Am I already sharing? Okay, good. Okay, let's get started. So, so this is I think a workshop in the lab course. Although due to COVID-19, this year, unfortunately, we cannot do lab directly. So today I will do the lecture, and then next week will be lab performance, but you guys basically watch video. Okay, I will present from here, but not necessarily you do the real experiment. So just I want to remind you. So basically the so this year is a little bit unique since you don't do experiments, so I have to think a little bit. But anyway, basically this week and next week will be about a single molecule study, particularly one of the single molecule mechanism technique, the optical tweezers, to study how to use the optical tweezer machine and also how to analyze the data. So, why we use single molecule method. What's the difference between single molecule and regular other methods, particularly comparison about with biochemical methods? So we knew that many cellular processes like DNA replication, transcription, translation, recombination, or chromosome segregation, such processes are usually often carried out by a few molecules. And far from the displaying smooth dynamics, actually these processes can be stochastic in nature, which is actually molecule A starting time 0, but molecule B may start time 10 seconds later. We don't know. In biochemical data, we need to use many samples, many cells to combine. So in that case, I don't know molecular A or molecular B, molecular C, when it starts. Instead, we can only see average information. But single molecule allowed us to understand individual molecules movement. So we know molecule A starts from this time 0 to until there. Molecule B starts from another point to there. So that's the main difference. And this is a summary of the difference between bulk, which is like a biochemical, a regular method, and a single molecule method. So bulk method is instead of since using many molecules, actually activity are robust. That's the advantage of bulk assay. Instead, single molecule is, since we use one molecule at a time, of course, activity sometimes has a disadvantage by weak, such activity. Sometimes it's very noisy that hard to detect the one molecule. Of course, since I already said that in bulk, since we use many molecules, we can only see time and the population average. Instead, single molecule, we can see individual molecules movement. So sometimes even we can see stochastic movement or random movement as well. And in bulk, since we average it, so only we can see majority of the movement product. Instead, single molecule, we can see many movement. So this is not clear probably, so I will show next slide so that you will understand what it is. So right now, probably you guys cannot go Macau, sorry about that, but if you want to go Macau from Hong Kong, how to go, okay? Many people probably, you guys take, right now has a bridge, so probably can take bus from the like nearby airport that has a bridge, right? So can do that, that's one way, but some people take ferry, some people even take helicopter if you are rich, right? Such exists, such service. Only 10 to 20 minutes to arrive in Macau, so it's good. And maybe even some people go to Shenzhen, Guangzhou, and take train to go Macau, could be possible. So in bulk, what would happen from these, like people go from Hong Kong to Macau? Basically, probably I can imagine that more than 80% of people use bridge. So only in bulk show up as people take bridge. And other people's data is ignored because we only average the information, right? So that's why that's kind of considered as noise, but nothing we can find out. But in single molecule, since we count individual molecule, individual people's movement, so that we can monitor from person A use bridge, person B use ferry, person C use helicopter. So we'll understand even their case, like a helicopter, can get such data can be achieved. So that's the advantage of a single molecule rather than bulk. Currently, there are many methods. Are you okay with that? You have a screen. Okay. It's okay. It's okay. Telephone, you can see them. Okay. Yeah, it's okay. So there are several methods, the single molecule method. So in the listed in here. So technically, like people consider AFM, like this is imaging technique, but that's also considered as one of the single molecule method. It's a high resolution method. In addition, has a magnetic tweezers or tethered particle motions or optical tweezers, single molecule FRET, the fluorescence-based experiment, or super resolution imaging, state or storm, palm, many way to say, or spinning disk confocal laser microscopy. Some of them in the BioCRF, I believe, in the particularly in the super resolution imaging, but that's also considered as one of the type of single molecule studies. So, I mean, there are many methods. Each one has a, the advantage and the disadvantage. But since only I will deal with optical tweezers, so basically I will show about optical tweezers. I mean, each one has advantage and disadvantage, true. But if you want to know, I can explain. But it's, this time I will only show the optical tweezers. So, so here is some video. Basically, optical tweezer. What optical tweezer does is simply this. Okay, so this has a bead, small particle. Okay, this like a less than 5 micrometer bead. Its bead is usually in the liquid, moving random, like a Brownian motion. Right? You can see moving Brownian. So this is the normal condition. Okay. In optical tweezer, basically using laser to trap such small bead, and we can do this kind of funny movement. We can manipulate the bead, basically. Small particles. So you can see some round, we are moving. We cannot see the laser. We are using laser, but we cannot see the laser. But because we put some filter, but we could do many ways to manipulate the beads. Okay. I mean, this itself is no scientific meaning, by the way, just in case. So I cannot explain what is going on, but basically just wanted control the bead. Okay. So that's what they can do. Basically, just using laser to trap particles, and then so that's the method. Optical tweezer. Okay, so this video fine. Yeah, whatever I can do. Yes. Anyway, okay. So this method using optical tweezer is actually the inventor of the optical tweezer actually got the Nobel Prize in the 2018 in physics. So the person in the Arthur Ashkin, so he's in Bell laboratory, and Arthur Ashkin is for the optical tweezers and their application for biological systems. So, and the other two co-receiving, they are completely different reasons actually. But basically, this they are actually for their method of generating high intensity ultra short optical pulses. So for some, this actually even I don't know what it is actually because I'm not physicist or physics person. So, but some even can use for eye surgery each thing. I think I remember. So that thing. But so I will focus on the explaining about Arthur Ashkin. So he is actually, you're surprised that in the optical tweezer itself is quite long, found out quite a long time ago, actually. In the 1970, actually. So 50 years ago from now, right? So quite old method. Actually, he's in fact still active. He was born in 1922, just in case I could tell. Okay, so this is some interview. I think this is just a radio, I think. No, video, sorry. In 2014, sorry, like 6 years ago video, okay? So how it looks like Arthur Ashkin. So he's not. Voice is not important, so I just, we could hear, hopefully.
We're moving to the field of laser trapping and cooling. We all learned that light has a momentum, but can it be used to manipulate objects? After Ashkin will talk to us about the
I got
ideas of
PCR
laser
too.
trapping and manipulation of particles
Oh.
by lasers.
I consider it a pretty great honor to be invited to speak at this symposium. He was my friend and he was a colleague. I'm asked to speak about what I did with Jimmy in the early days of laser trapping. Now, I consider this work to be the most interesting
I load
of my whole career. Its
I
origin,
load
however, goes
everything
back
5
long
microliters.
ways.
So
70
even
years
the
to
diluted
start.
IP 5. Okay.
Of the audience, I was 20 years old at that time and a sophomore physics major.
Anyway, so he's I just want to show that he's still active, so that you guys are still young, but if you want to work, even almost 100 years old, so still can work. Okay, and in fact, his Nobel Prize, the work is in 1970, so which is actually already he was almost 50 years old, so quite old actually. And you can even take a look about, we can listen the voice of Arthur Ashkins in the moment of the Nobel Prize. It's actually very interesting statement he did, so maybe let's take a listen. It's about 4 minutes voice.
Hello. Good morning. Yeah, who is this? Well, my name is Adam Smith, and I am calling from nobelprize.org, which is the website of the Nobel Prize in Stockholm, Sweden. Okay. First of all, many congratulations on the award of the Nobel Prize. Okay, thank you. May I ask how it feels to be the oldest ever awarded laureate? I didn't realize I'm the oldest ever. So I just about made it, huh? Because you can't be dead, and when if you were a winner of the National Inventors Hall of Fame, you can be dead. And I won that prize a couple of years ago, and I was very proud of that. That is the most, I would say, most important prize I won. May I ask, are you still experimenting in your home lab? I am. In fact, I'm writing a paper now that you guys are disturbing in my, I'm going to send it into science and hope that they'll accept it. Well, I guess that's the secret of a successful research career, to concentrate on work rather than distractions. Well, that's my hobby, more or less. I was interested in science since I was a kid, so I tell my wife that that's the only thing that I'm really good at. And presumably, you're amazed and delighted to see the variety of applications that optical tweezers have been put to. Well, I anticipated that it was pretty important from the day go. The thing that I love, well, one of my heroes is this guy, this Dutchman Anton Leeuwenhoek. He's the guy who discovered animalcules, and he kept writing to the Royal Society, telling them and sending them pictures, and nobody paid any attention to him until very much later. They want a sample of his microscope, and he said, no. Because if you want one, you have to do it yourself. He's a hero, and there are other guys like Michael Faraday, who's another one of my heroes. It's good to have scientific heroes. So you knew when you developed them that you were developing the instrument that would allow you to probe molecular processes. Yes. Well, look, I was interested in trapping molecules with light a long time ago. I mean, my famous paper in 1970. That's the most
famous paper I ever wrote. In that I mentioned molecules with light. But I never thought living things. Light was supposed to kill tissue. They used light as to heal wounds, and it was considered to be deadly. So that was very much a surprise. That was a big surprise, and once I got a lot of old stories though about what happened when I described catching living things with light. People said, "Don't exaggerate, Ashkin."
You certainly weren't exaggerating. How exciting. Well, we look forward to hearing some more of these stories. Will you be coming to Stockholm in December to
I'll
receive?
come if I can.
Sure.
Okay, so basically I particularly wanted to emphasize that not the part of the later he said something can trap the biological sample, right? That's the point, but in addition, I want to mention that even though he was at 2018, he was 96 years old, but he was writing paper to try to submit the scientific journal, some journal, right? So that's very admiring. That's very, impressive, I think. So you guys' career is quite long, yeah. From now to think to 96 years old or 98 years old now, he's still alive, so he's still active. So that's the very important information I want to tell. But anyway, okay. So basically, again, the optical tweezer is using light to manipulate object, which I show in the video. Like some small particle can move whatever way, right? Control. And this itself, optical tweezers, invented by Arthur Ashkin in 1970, long time ago, 50 years ago. So basically, you can take a look here, statement about the particles with high index of refraction, like a glass or whatever thing, beads, are attracted to intense region of laser beam, focused through a microscope objective, and can be held permanently at the focus point. So basically, using microscope to focus, right? Microscope has a light to focus. So that's focus point. Some object we hit will be trapped. You'll see some video later. So because not necessarily I'm good explanation I can do, because optical tweezer is more physics equipment. So I'm not so much trained in the physics background. So, but you listen some video later. But anyway, basically, this is a paper in 1970 in Physical Review Letters. Arthur Ashkin himself published in Bell Institute. So basically, you can see this is the title, Acceleration and Trapping of Particles by Radiation Pressure. Anyway, what he did is he put the light and focused and tried to trap in the liquid condition some small particles. That's he did. That's a Nobel Prize work, actually. And then, actually, Ashkin keep studying. He was interested in something about biological samples. So what he did is this is science paper in 1988, published optical trapping and manipulation of the virus on the bacteria. So as of 1970, even though invented, didn't know how to deal with biological sample because he's not biologist actually. So in this 1988 paper, actually using laser to try to trap virus and bacteria. So you can take a look, left panel is basically the virus trapping, and right panel is the bacteria trapping panel, okay? So in the left panel, you can see in the top, this one, increase. Increase means trap one virus, trap second virus, trap third virus. And once B means something stop, light, so that's going to be release virus again. And then trap again one, 4 virus, no, 3 virus, and then release. This can do it's whichever this lower panel is just the power is become weak condition, so that still can trap. And in the right panel, actually, you notice something, noisy, way noisier than this. Do you know why it is noisy? I see. Could be, but in the reality, I think this is the molecular size. So because virus is small, bacteria E. coli is 1 to 4 micron, virus is 30 nanometer. So it's a big try, right? So the laser is focus very small. So bacteria can move, even try to trap. It's a huge, can move, right? So that's the point. That's why it become noisy, okay? And more importantly, the Ashkin increase the power to about 50 times more in here. And very less noisy in the around here because power is strong, trapped. But after that, something break. Do you know what happens? Do you know Zoom people? People in Zoom? Or people in classroom? So the answer is basically bacteria die because using strong power, laser itself, right? Strong laser will kill bacteria because that itself is a heating temperature too, cause temperature, right? Heating temperature. So that's why dead. So they learned from this study that actually to use optical tweezer to use biological sample actually have to be careful for power of laser or a temperature, etc. Because Ashkin is actually physics person, so he didn't know such difference. Simply he thought just based on the size, but that's not only the issue. So that's an important point that he learned the lesson about that. So, okay. Because optical tweezer actually can be used. It's a half of the optical tweezer people. Actually, it's not the biologist, it's physics people. Completely different thing to use. It's not biological sample anything actually. Even I don't know what it is, detail, I cannot explain, but they use some physics stuff, even now. So that's purpose also possible to use, but for biological sample purpose. So for physics purpose, actually stronger power is better because stronger power is less noisy. For example, E. coli, if you have a stronger power, more trap correctly, not moving. That's good. But in biology, cannot do that because die. So we have to be careful about that. So I didn't explain the principle of the trapping. So I showed the video. I don't think I explain is not a good idea. So I think using video to explain, okay? Yes. Because biological sample, right? Okay, that's a good question. So this one is, this point, their point, initially they didn't care such thing. They thought maybe they can, for example, can use for trap and separating. For example, can use for sorting, right? Cell sorting. For example, trapping the bacteria, move to another place because we can manipulate whatever place, right? And release, and going to be fraction A or fraction B. So such purpose, for example, if it's dead, you don't want to be dead. Right? So technically, optical tweezer can use for such purpose too, even though the example in the next week, I don't show such thing at all. Or in the inside to molecule to move drug delivery system, it can be useful. But let's take a look at the principle of trapping. Okay. So since voice function doesn't work in here, so I have to be careful about this.
Light exerts force on matter. This effect can be seen in the tail of a comet, which always points away from the sun throughout its orbit, because the comet particles are pushed away from the sun by light pressure. James Maxwell first explained that light consists of transverse electromagnetic waves. Maxwell's laws show how such waves can exert a longitudinal pushing force against matter, and thus they carry linear momentum. Light waves consist of electric and magnetic fields that are transverse to the direction of propagation. When light hits an object, its electric field interacts with an electron in the matter and causes it to move. This is the electron. Here, the electric field is drawn vertically, and so is the electron motion labeled V. Such electron motion is responsible for refraction, reflection, and absorption of light by matter. Note the electron motion is also passing through a magnetic field associated with the light labeled B. Such motion through a magnetic field generates a Lorentz force on the charged particle, shown by the green arrow. Maxwell's laws tell us when a light wave with energy U is completely absorbed by matter, such a Lorentz force will impart an impulse of momentum to the matter, where the change in momentum of the matter, delta P, equals U divided by C, the speed of light. Later, with the advent of quantum theory, it was seen that a single photon carries with it an amount of linear momentum equal to Planck's constant times the wave number, or the inverse wavelength. In the late 1960s, many labs were using their new toy, the laser, to explore the nature of light. They tried to measure light momentum by various means, such as reflecting laser pulses off mirrors on torsion balances. But Arthur Ashkin at Bell Labs discovered the simplest and most useful technique for demonstrating light momentum effects. He suspended micron-sized refracting particles inside of a liquid, and when the particles came close to a beam waste from a laser, they were drawn vertically into the waste and expelled out the backside. He explained how the sideways attractive force was in fact a gradient force, sucking the particles toward the most intense part of the light, and how that the force that forced the particles out the back of the beam was a scattering force. In order to make a stable trap and hold a particle stationary, he had to make two counterpropagating laser beams that met in the center and held the particle in a stable position. To understand gradient and scattering forces, consider a refracting sphere that is hit by a photon near its edge, such as this photon with momentum labeled Pn. The particle acts as a lens, and the photon is refracted through an angle theta. It now has a new momentum, P out, and a difference in momentum, delta P, shown here. Since momentum is always conserved, the particle receives an equal but opposite impulse. For a stream of photons hitting the top edge, such force is primarily upward, so it moves the particle toward the intense beam. This is the nature of the gradient force. However, there is a slight tilt to the force vector toward the right, which sends the particle away from the source of photons, hence the so-called scattering force. We can create a simulation to show what Ashkin did and demonstrate it. You can download the simulation from the website. It's called Photons. And indeed, these yellow streaks are the photons of light going by, and the blue circle is a refracting bead. Now, if we do what Ashkin did and get the bead close to the edge, it is sucked into the pencil of light. So that is a gradient force that is sucking it into the intense part, and then it is scattered downstream away from the light. So if I put the bead back in the middle, notice that the momentum, forward momentum of the light is reduced by the bead, and the bead reacts by moving through the water toward the right. Again, in 1986, Ashkin and coworkers made a major advance in the trapping field by demonstrating a stable single beam optical trap. Here, the bead sits just downstream of the laser focus. Any scattering force from, say, reflected light, these dotted lines are the reflected light, any scattering force that would push the beam out of the trap is compensated by a refracting effect, where the beams that go through the lens, through the bead, are refracted into a narrow cone forward. This increases their downward momentum, and that, in effect, pulls the trap upwards toward the focus. So there is a balance between the scattering forces and the refracting forces, which increase the forward momentum of the light, and the bead comes to a stable position in the single beam trap. Again, we can demonstrate this using our simulation. Here we see the simulation in which the bead is captured in the single beam trap. And you see it sits just beyond the focus. In fact, we can apply a transverse force to the bead like this. This little red arrow is the force, and the bead will hold against that force. However, there is a kind of a weak spot in the backside of a single beam trap, and it doesn't take too long before the bead wanders out of it. You can improve this situation if you have a dual beam counter-propagating trap, which we can also simulate. So this is the same total intensity at the focus, but half of the power is in two beams that are counter-propagating. Then if we put the bead back at the center, it stably holds that force. And indeed, it will hold a great deal larger force than the single beam trap would do at the same light power. But how can we measure the force exerted by light on a trapped object? Ray photometry gives us such an opportunity. There we measure the angle and brightness of all the rays entering and leaving the trap. Then we can apply trigonometry plus Maxwell's formulas for light momentum to obtain the axial and transverse force acting on the particle. The trick lies in collecting all the exiting light and scoring the rays properly. Here is a picture of a simplified counter-propagating optical trap. It consists of two lasers sending out two beams of light focused by two objective lenses, and they focus at the same spot in the middle. These are polarization optics here, the polarizing beam splitters and quarter wave plates, that ensure that the light from this laser goes through the objective, through the trap, collected by the other side, and onto this position detector called a PSD. Likewise, the light from this laser travels through the system and goes onto this PSD. A PSD is a silicon sensor which is built in such a way that it gives two signals showing the offset and the brightness of the light in the X and the Y direction. These are the properties that we need to score the light momentum flux that is imparted to the light by the object in the trap. Here's a schematic picture of how a trapped object deflects light when it's in the trap. This plane on the left represents the left objective. These dotted lines are the maximum collection angle of the objective, or the numerical aperture. Here is the particle in the trap. And here, in this cone, is a narrow beam of light, which is not filling the objective lens entirely, trapping the object. If there is no force on the object in the trap, then when the light comes out of the right objective, it is centered on the PSD detector. If indeed there is a force, as shown on the right, then that force deflects the object in the trap, and the object refracts the cone of light to be offset on the PSD detector. We can also use that same cone of light principle to detect the forces along the optical axis, the z-axis of the optical trap. So if the laser beam is brought to a focus and traps an object, and there is no force on the object along the z-axis,
well,
then the cone of light is the same size as it when it went in. However, if there's an axial force in the z direction forcing the particle toward the direction from which the light is coming, the cone of light comes out larger. This is a reduction in the momentum along the z-axis of the beam of light. If the particle remains trapped and there's an external force on the particle in the same direction as the light is shining, the momentum of light is increased and the cone comes out smaller. These effects can be used to score the z-axis force on the trapped particle.
Okay, quite a long video. Thank you for watching. Actually, I hope you understand, because I'm, but it's don't worry, even you don't understand, it's okay. It's not a problem at all, because we don't, we just use machine. That's it. Yeah. Just if you are curious, you can take a look video so that you know what's really going on in the optical tweezer, because otherwise, it's hard. But we actually, the biologist point of view, all we have to be worried about is temperature and a couple of things, okay, using optical tweezer. So one thing is temperature. So temperature is critical for biological sample, because DNA or protein, or RNA protein, for example, if it's heating, protein will be denatured. So not what we want to see, can see. Or DNA, of course, heating also double strand becomes single strand. That's not good. Or RNA, for example, RNA usually forms secondary structure. That will be messed up if we heat it. So temperature is important, no matter what, right? So another thing is laser. So in physics study, in optical tweezer, whatever wavelength laser technically can use. But in biological sample case, actually we have a very limited range of sample can use. So here showing red, show that red is the hemoglobin absorbance. Okay, so hemoglobin is absorbing the light around 300 to close to 1,000, something like that. Basically, the region that absorbing, we cannot use. So you can see that if we use around 400, the hemoglobin itself absorbs the light, so will be heated. So in fact, our laser is IR, which is actually around 830 to 840, or some lab use, or even my lab also use 1064 nanometer this laser. Because this region, you can see that 830, it's not high, so high, the absorbance of the proteins, or DNA, or RNA. So that's important. And also not so high in water as well, because most of the biological sample need to use water, right? Or buffer, but the buffer contains water, like liquid. So we also don't want to absorb the light in the water, because absorbing means cause heat, temperature increase. That's don't like.
Did you put away the filters?
Kind of acceptable range. If we go more 2,000, 3,000, much higher,
the
not
box
good.
of
The water
filters and the
or
mesh
500
and the
also the protein
caps
of loss,
are not.
right? That's the reason
Not at
we
the.
use the optical tweezer in biological light laser source. It's very important.
And I didn't put the caps are still.
Oh, I see. So
this is too detailed, so it's probably I
put them on the shelf.
Lecture, but
you can take a look. I don't know if they're dry yet, but
I
can't find the box of caps.
How to say that? This is the kind of always we need to debate the laser power, how strong, and how to say that? How strong laser power and the relationship with the lifetime of biological samples. So of course, stronger power is better for the whatever sample measure, because stronger power means more trap strong here. Less power is of course hard to trap. So stronger is better, always better. However, stronger, of course, even though we are using
is this even
limited?
I can't see.
How to say that? Wavelengths. I mean, we are carefully choose the wavelengths around 830, for example, right? But still absorbing some amount, right? Of course, absorbing some amount. So then, if we increase
more
the power, so basically the lifetime of biological sample. In this case, basically DNA. Basically, DNA is trapped. DNA is in the end. I'll show more detail next time. But basically, in the one end has a biotin, and the other end has a decoxygenin. And biotin is trapped by streptavidin bead, streptavidin coated bead. So we call it SA. And the other side is the anti-decoxygenin coated bead to trap optical tweezer. So this DNA handle, how long can keep? So if we increase power, automatically break, die, basically. So you can imagine that the increased power, decreasing black light, basically you can see, right? Of course, we have some solution or improvement to do that. So of course, we want to increase power because power is more or less noisy. I mean, the better, stronger trap. It's good, but we lifetime decrease, right? So technically, we can improve the lifetime by adding some chemicals that absorb, for example, some active oxygen, etc. thing. But still, we need to worry about such thing, okay? Because the active oxygen absorbing some chemical itself may cause biological reaction too. So it is, we need, when we use a biological sample, we have to think many conditions. So that's the I want to say, oxidative damage, so that when we use stronger power, also create oxidative damage. So that's cause to messed up the lifetime will be affected. So once added some chemical, actually, what's that? What kind of chemical? The one is, I think, I forgot what it is. H2O2, I think, yes. I forgot the name, but that can increase, for example, green. So increase the lifetime, same power here. Around without chemical is around 30 seconds, but with chemical become to 200, 300, 400, 500, 600, 700 seconds. So that's good. And then not so much need to do more. I think don't need, okay. So then, what else I need to show? So frequently, when we do the optical tweezer, frequently we use DNA as handle. Okay, it's even we use some protein pooling, something to know protein folding structure, or it's not necessary to need to do DNA-related event, but we still use DNA or RNA as handle. Handle means you can see between two beads, something need to be connected. Of course, in this session, we plan to do nucleosome, okay? Nucleosome is the histone is bind to DNA. So directly we need DNA anyway, but the even non-related DNA case, usually we put DNA between both hands. And what else need to know? Then this one maybe. In addition, actually we know that when we pull DNA, so basically we stretch DNA, you will see next lecture, so you know exactly. Basically we move DNA, okay? We move bead, we move the bead to the left to right. So laser trap can move. So that's a manipulating time. You see in the video, left to right, moving. So DNA will be stretched, right? Tension. And then at that time, you can see that pulling, you can see tension, force, create force. And then as we know, double-strand DNA, if we know when we pull double-strand DNA and the single-strand DNA, the response is different. So you will probably see in the next lecture video how double-strand DNA and single-strand DNA behave. But
It's going
basically,
to stick
I
with
want to show
the-
you that when we pull double-strand DNA like behavior up, and once it reaches to 60 piconewton, around 60 piconewton to 50 to 60 piconewton, usually double-strand DNA itself is peeling and becomes single strand.
Because it's
So this is showing us
right?
overstretched
I just
transition.
don't
It
know
becomes
if
single
it's
strand.
It should be okay. It should be okay.
And they come back.
The color is slightly different here.
So like that. Okay. Sometimes come
why
back,
is
sometimes
there
just
more?
But
Interesting.
you'll see this kind of
That
behavior.
was, did you suck up
the
like
next,
leaving 5?
I suck up everything. Supposedly.
So
Okay. So what I do is similar to M2Bs.
So
suck up
the
like
next week,
leaving
I will show the
50
how to make,
centrifuge
how to do the optical
to
tweezer assay
completely,
in the nucleosome. Okay, the nucleosome.
So possibly
pulling
those has the liquid on the wall.
And then I'll skip
So
inside.
you suck up from the bottom, but
Just an example,
so like
what kind
the
of
color
tweezer
is
assay can
slightly
start.
lighter.
This is, if you are curious, you can take a look. For example, kinesin, dining movement, so that how much dining or kinesin can move.
I should, next time I
Such
should
details we can study. For
leave
example, this one can
a
study
little
about
bit
this is
and
kinesin
do
movement.
it,
So you can see
and
moving kinesin.
remove
So
everything.
we can see real time of the
dilute,
movement of the
Right,
kinesin.
right, exactly.
and then boil.
But
Okay.
at least those are fine.
Or
so,
same again,
oh,
kinesin movement,
Why
or
is
even
this
can
too?
do about
Why is it
RNA
so
polymerase transcription. So that how RNA
maybe
polymerase
the
moves
beginning
on the
or
DNA
the
chemistry.
last. I don't know.
Such study can be done by
Anyways.
optical tweezer. That's a two example I showed that. And in addition, we can study, particularly in this case, we study about nucleosome.
Easy to.
So basically, we do in the eukaryotic
It's just
genomics,
a
we make that by
carelessness
the
thing.
nucleosome, as you know, probably. And then basically, histone 2A, 2B, H3, H4, it makes an octamer to wrapped by 147 base pair of DNA. And then basically, this date is incorrect, sorry, ignore it. But basically, we trap, okay, we'll make this kind of construct. The detail I will explain in next week, so don't worry about detail. But basically, one side of trap, or pipette probably we use, will be decocctioning and anti-decocctioning, okay? The other side is just biotin and streptavidin. And in the center has a nucleosome. Once we move trap, right side move to that, nucleosome will be nucleosome histone and DNA interaction with break. And we can see as loop, like something DNA loop. And we quantify how that loop, for example, force or distance, to understand the stability of, for example, nucleosome. Or we could quantify the stability of the nucleosome. For example, this is one of the examples show that actually you guys assignment is a similar thing. So technically should need to know, but basically this is nucleosome wrapped condition. And the first 3 piconewton, something unwrapped, black line, black dot. So this is actually come out the H2A, H2B dimer from DNA interaction with the break. And then if we keep putting a force more, break again. So this is basically H3, H4 DNA interaction break. That's a strong one, okay? Force showing here is not necessarily, you will see on next week, the example trace is quite different probably, because this is affected by the concentration of the salt, etc., or speed of the pulling. And once pulling, you can see that in the red is go back, okay? Go back, releasing. So that the force will decrease. And following this line, so still no interaction, anything. But you see something suddenly back, one back, two back, and back to normal. And sometimes we can keep repeating this pulling behavior. And relax. And we can collect the data, what the force this nucleosome unwraps break the histone DNA interaction. So that will be the very likely your assignment actually. So next week is basically I'll show you the how to make nucleosome. Then after that, we'll put that nucleosome to put in the optical tweezer machine to see this kind of leap that how this nucleosome is unwrapped. Okay, so that's you'll see. But I will explain detail in next week. Usually, we could show directly to you guys the machine so that you can even touch or handle the pulling. But unfortunately, this year cannot do it. So we'll shoot some video about that. Okay, so that's today's lecture. And then, do you have any questions? And regarding the assignment, I will also talk in the end of the next lecture, but next lecture is very relevant, how to say that. Exactly, I will show demonstrate how to do nucleosome unwrapping, and that's data you guys will analyze the data basically. So analysis of the optical tweezer data is that will be the you guys assignment. And I'm not, I mean, probably I may give you not everyone to be same data. Actually, I may give you randomly distribute a couple of type of data that you cannot just copy and paste to send it. Okay, so you have to do it. That's what happens. But the details I can talk on next lecture, next time.
Hi, I have a question. Can you hear me?
Do you have any questions?
Yeah. Hi. Can you hear me?
Yes.
Can you hear me? Do you
I
have
think
some...
I cannot hear the voice. So can you type in chat?
Oh, yes. Okay.
Somehow voice is not working. If you have any question, please type also other people too, okay? So that I can answer that. I think you guys are more familiar to use chat rather than my generation, so prefer that, right? So I think. When I was a kid, didn't have such function, so we had to only phone call. Not true, even didn't have a phone call, cell phone. So. Do you have some lectures or video on this argument? I'm not familiar with this topic and would like to understand better. I see. So, interesting. I see. So the question, you can take a look in the chat. So this argument, you mean this argument means, you mean principle of optical tweezer or like about the nucleosome, or what's exactly this means? Can you a little bit specify? Single cell analysis, single molecule analysis, you mean? Single cell analysis is a more different thing, I think. Yeah, single molecule analysis, usually, so you mean comparison among several methods? Or I see. I don't know, something basic or in order to have some general idea. So okay. So basically single molecule itself, just I want to remind you that single molecule itself, why people do that is because can do, for example, understand this kind of thing. So that basically one molecule's behavior, that's different from bulk. Many molecules, if have many aggregated molecules. Because we know individual molecule A started from 10 minutes to do some reaction, but molecule B maybe started from 20 minutes. And maybe speed of some reaction is not same actually, but people knew it's not same individual molecules. So that's one of the reasons people want to study single molecule. And one of the reasons, for example, high resolution imaging people want to do is because super resolution, of course, people think previously co-localizing between two proteins in normal machine. But super resolution can find out even that's really true or not. And also, for example, that's reaction. How many molecules are involved? Even can count that's like a whatever reaction. I don't know, destruction enzyme or whatever reaction. How many molecules are required for this accumulation? That's even using super resolution imaging, for example, can do that. And then, of course, I said individual the methods are completely different. That, for example, atomic force microscopy is resolution the best, to be honest. So it means you can see even 1 micrometer of movement, etc., individual. That's better than super resolution imaging. But only problem with the atomic force microscope is we don't know any fluorescence or nothing. So it means only black and white more. So it means that dot, what we need to know, what is that dot? What is that? Okay. So that's more complicated because sometimes we do like some experiment, right? But we need to know what it is. What is that in advance? So if you are labeling fluorescence, for example, you can see molecule A is binding DNA or something. You can find out by fluorescence level. But atomic force microscope don't have such image, just has the image binding. But does molecule A or molecule B is unknown. You need to know in advance somehow. That's a disadvantage, right? Like magnetic tweezer is similar to optical tweezer technically. I mean, detail, I don't want to discuss so much. So, but has some advantage, disadvantage as well. And tethered particle motion also same. Technically, don't use optics, but using some DNA with B. Basically, some random movement of the DNA to measure the difference. So more noisy. It's not popular, as I can say. And single molecule FRET is a FRET, which is actually the basically you want to measure the distance between two proteins, right? If it's close, then don't have to accept that of the distance, right? Matter, right? That's regular FRET. Many people use it, but that's changed to single molecule. That's commonly people use. So because that's advantage is that single molecule, of course, one molecule. So really distance or not average distance can be measured. This advantage is since one fluorescence molecule behavior, movement, transfer, right? So of course noisy. It's very hard to distinguish from background noise. So that's the more or less the method-wise, the comparison among these methods difference. So depends on what kind of experiment you may have to choose the different method as well. Sorry, actually, I don't know what I can really explain about the basic so much. So hopefully a little bit better understanding. Any other question? But you can find from also website too. If you study a little bit, if you're curious about that, can. And most of the technique method itself required some physics and background actually, because all machines are invented by physics people. So these guys are. It's not a biologist. So yeah, my explanation of optical tweezer will be crappy usually. So basically, my case, I just say something laser trap and another bead doing like a DNA as a string, like a string. So we can measure based on string force, etc. Optical tweezer itself is like something like that. So anyway, do you have any question? If you have any question, you can type it now, or if you have any question, even next in the beginning of next time, also fine. Or if you have from the classroom, also fine. You can say directly to me. That's also fine. I can hear voice. If no particular question, then I think next week I already mentioned the assigned time, right? Set up the time, right? Okay. So then see you on Zoom or classroom. Okay. So then today's class is dismissed.